Hello students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to introduce before you a waveguide. As we know that waveguide is a very important tool when we studied about the microwave, because basically waveguide are designed for the transmittance of signals in the waveguide in the microwave frequency. So, what is the waveguide? Waveguide is basically consists of a hollow metallic tube and of rectangular or a circular shape which is used to guide an electromagnetic wave. So, when we say that it is used to guide the electromagnetic wave, that means it comes under the category of bounded medium, and it is of metallic tube and it is of rectangular or a circular shape. So, basically there existed two type of a waveguide. First one is the rectangular waveguide and the second one is the circular waveguide. Rectangular waveguide and this one is the circular waveguide. The name of the and the type of the waveguide basically depends upon the shape which is it have. In waveguide, the electric and magnetic fields are confined to the space within the guide and no power is lost through radiation. As we have seen in the case of a transmission line also, or in the case of a strip line in the last lecture, that there exist a losses due to radiation and we have to apply certain conditions to minimize that losses which occurs due to radiation. But since the electric and magnetic fields are in this are confined within the guides, that is why the loss due to power loss due to radiation is very much less in the case. Dielectric loss is negligible since the guides are normally air filled. When the guide is normally air filled, so the dielectric loss is also negligible. However, some power is lost in the walls of the guide and that loss is very small. It is used to propagate several modes of electromagnetic wave within a waveguide. Several modes of electromagnetic wave means several frequencies of the signals or of the at microwave frequency are possible to propagate inside a waveguide. But and how these modes are calculated? These modes correspond to the solution of the Maxwell equation and we will go in depth in this section. And which frequency and the which wavelengths are can pass through a particular waveguide depends upon a dominant mode. Dominant mode is basically the particular guide having the lowest cutoff frequency. So, already we know that a waveguide basically acts as a high pass filter. So, the minimum high pass filter means that it is able to attenuate a signal below a particular cutoff frequency and allows all the signal above that particular cutoff frequency. So, that cutoff frequency plays a very significant role in the case of a waveguide and the mode at that particular cutoff frequency is called as the dominant mode. So, basically we can say that dominant mode definitions as well as its significance plays a very important role in the case of a waveguide. So, again I am repeating, dominant mode is the particular mode which is having a lowest cutoff frequency in a particular waveguide. And since our waveguide behaves as a high pass filter, so it is able to attenuate all these frequencies below a cutoff frequency or we can say below a dominant mode and allow all the modes or all the frequency above a particular cutoff frequency or a dominant mode. The process, so we can see in the last slide that we are able to calculate the modes of from the Maxwell equation. The process of solving the waveguide problems involve the three steps. First, Desired wave equations are written in the either rectangular, cylindrical or the spherical coordinate which is suitable for us. Boundary conditions are then applied as per the conditions which is available to us. Then the resultant equations are solved in the form of partial differential equation either in the time or the frequency domain. So, the first step which we have to see that we have to know the wave equation. Already about that we have studied. A rectangular waveguide. Now, there exists a two type of a waveguide. So, first of all we will deal with the rectangular waveguide. A rectangular waveguide is a hollow metallic tube with the rectangular cross section. If it has a circular cross section, it will comes under the circular waveguide. The conducting walls of the waveguide confine the electromagnetic fields, thereby guide the electromagnetic wave. This is the basic property of the any waveguide. When the waveguide travel longitudinally down the guide, the plane waves are reflected from the wall of the wall to wall. What we are seeing here, from this wall it is reflected, again from this wall it is reflected, and again from this wall it is reflected. So, the reflection continues. This process resulting in component of either electric or magnetic field in the direction of propagation of the resultant wave. So, during this some waves propagation of the resultant wave occur in the direction of propagation of the wave. So, what we are saying that then due to this process, due to this continuous reflection, electric field and the magnetic field component exist in the direction of the propagation of the resultant wave. So, there does not exist a TEM. TEM stands for transverse electromagnetic wave. And in the case of a TEM, we does not have a, we have a both Ez and Hz equal to 0 in the z direction, which is the direction of propagation of a wave. That in the TEM mode, what is going to happen? In the direction of propagation of a wave, the electric and magnetic components both are 0. And here we are saying that due to the continuous reflection of the plane wave along the due to the walls, from the walls of the waveguide, there exists a component of electric and magnetic field in the direction of the propagation of wave. Then what does it mean? There is a chance that either Ez or Hz exist in the direction of the propagation of wave. That is, if we are assuming that the wave is propagating in the z direction. So, the modes which are possible in the case of a waveguide is basically our TE and TM wave, transverse electric and the transverse magnetic wave, and TEM mode does not is possible in the case of any waveguide. Till now what we have seen that in the case of a transmission line, we have the mode which is possible, that is TEM, and the case of a microstrip line, quasi TEM is possible, but in the case of a waveguide, TEM mode is not possible. The mode which is possible is T or TM. And since the wavelength lambda is in the direction of propagation of incident wave, there will be one component lambda n in the direction normal to the reflecting plane and another YP parallel to the plane. So, what we are seeing, we are able to see this in this since if we are assuming that this is the wave. So, this get break into two component, first this lambda p and another one lambda n normal and lambda p parallel. So, in this line basically we are talking about this line lambda and lambda p and this is lambda n, two component. So, now lambda n can be written as lambda upon cos theta, where theta is the angle of incidence theta, and lambda p is equal to lambda upon sin theta. Now, so what we are having? Due to this, one standing wave in the direction normal to the reflecting wall, that is lambda n, and one travelling in the direction normal to the reflecting walls. So, in the lossless waveguide, the modes may be classified as a TE, transverse electric, and the transverse magnetic, and are basically designated as TEMN or TMMN, where M denotes the number of half waves of electric or magnetic intensity in the x direction, and N denotes the number of half waves in the y direction. So, when we take a wave, this is called the full wave, and when we draw the direction, when we have a full wave, that means one in the positive direction and another flowing upwards, another flowing downwards. And when we talk about the half wavelength, one full wavelength gives two half wavelength, half length up till this only, half wavelength up till this only. So, when we talk say TE 2 1, what does it mean? Two half wavelength in the x direction and one half wavelength in the y direction. When we say TE 01, that means no half wavelength in the x direction and one half wavelength in a y direction. So, sometime you will able to see the diagram also of this. That means only one half wavelength, because direction is in one direction. And when we say two type of, that means two half wavelength, because one upward, one downward. And now comes the solution of the wave equation. Already we have said that for what are the conditions for finding out the solution of the wave equation. First of all, we have to write the wave equations, then we have to apply the boundary condition, and after that we have to apply the partial differential equation method. So, there are time domain and the frequency domain solution for each wave solution. For the simplicity, the solution to the wave equation in 3-dimensional, that is 3 dimension means that we are x, y and z, plus a time varying variable is taken into consideration here. This is a rectangular waveguide in which we are assuming that our wave is propagating in the z direction and a waveguide is in the xy plane. So, our assumption should be clear that our waveguide is in the xy plane and the wave is propagating in the z direction. So, these are the two equations of the electric and magnetic wave equation in the frequency domain. Del square E is equal to gamma square E, del square H is equal to gamma square E, this gamma square H. This is the electric field equation and this is the magnetic field equation. So, the only difference when we write the wave equation in the electric field, it will be del square E is equal to gamma square E, only terms is E, and here when we write in the terms of magnetic field, del square H is equal to gamma square H, and gamma, which is our propagation constant, is given by this expression. The general expression for any wave equation is given by del square psi is equal to gamma square psi, which is the Helmholtz equation. And when we write it in our rectangular coordinates, then it can be written as del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square gamma square psi. So, del is replaced as del square del x square plus del square del y square plus del square upon del z square, and when we multiply with the psi. This is a linear and inhomogeneous partial differential equation in the 3-dimensional. So, what we are going to assume here, first, so what we have done till this, first we have written the Maxwell equation, wave equation, and then we apply the boundary conditions, that is our, this is applied for the rectangular coordinates in the, now we are going to solve it by the method of separation of variable, because we are getting the partial differential equation. So, for this purpose we are assuming that the solution is given by psi is equal to x x, y y, z z, function of x in the x coordinate, y coordinate, z function of the z coordinate. So, now what we are going to do, we substitute this value in our equation 1, and what is our equation is 1? So, when we substitute, what we are having, del square, I am just now what we are going to do, we already know that these two are the functions of the y and z. So, what will happen, y y, z z comes in front, and we will have the double differentiation of x x only. Able to see this? Similar case happens with all the other functions, these two, these three, these two also. And now, when we divide this expression, the expression which we get next, when we divide that with x x, y y and z z, we are having this expression. So, what we have to do? First we have to substitute this expression in our equation 1, and after that we have to take the constant outside, and within differentiation we will take only that function which can be differentiated, and after that we will divide the expression with again with x x, y y and z z. So, in the denominator side, numerator nothing, 1 only, and in the denominator x x, that is why this way. Similarly, you are able to this get the complete expression. And since we are seeing that in this expression that this 3 terms is equal to the constant. So, when these 3 terms are equal to the constant, what does it mean? That each term is independently variable, and it follows that each term must be equal to a constant. So, what will be the 3 terms now? Kx, ky, kz. So, what we are saying that 1 by x d square x by dx square is equal to kx square minus kx square, this will be equal to minus ky square, and this will be equal to minus kz square. So, we are having this expression, and so when we say 1 by x d square x by dx square is equal to minus kx square. So, d square x by dx square is equal to minus kx square into this x will come this side. Similarly, for all the others case, d square y upon dy square is equal to minus ky square y, d square z upon dz square is equal to minus kz square into z. And when we solve this, this will be in this form, x is equal to a sin kx x, y is equal to c sin ky y plus d cos ky y, z is equal to e sin k z z plus f cos k z z. So, the total equation will be what? Total equation is our xx, yy and zz, that is our this in the terms of x, y and z. So, the total equation is just by multiplying this 3 expression. You are able to see this expression clearly. This is our x, this is our y and this is our z. So, now if we are assuming that a wave is propagating in the z direction and the propagation constant in the guide, that is given by gamma z g, it differs from the intrinsic propagation constant, which is our gamma, and our wave is propagating in the z direction. So, in the place of yg can be written as y square plus k x square plus ky square, and this kz is equal to gamma square. So, this is the expression basically of the, so gamma square, and this is our cutoff kc, kx square plus kc square is equal to kx square plus ky square, which is our cutoff wave number. So, kc is equal to under root kx square plus ky square, and this is called the cutoff wave number. And for a lossless dielectric, we know that gamma square is equal to this one minus omega square mu epsilon. Then gamma g should be equal to what? Gamma g is equal to gamma square plus kc square, and here we can able to have minus omega square mu square plus kc square. So, gamma g will be plus minus under root omega square mu minus kc square. Okay. And due to this, there are 3 cases for propagation constant gamma g in the waveguide. First, there will be no wave propagation, and this mode is called the evanescence mode, and this mode is important because it is used to calculate the cutoff frequency. And what is the cutoff frequency significance? Already told to you that cutoff frequency basically decide ki above which frequency our waveguide will work. That cutoff frequency decide the condition that if we say that our cutoff frequency is 5 gigahertz, that means all the frequency above 5 gigahertz will be allowed inside a waveguide, and all the frequency below that 5 gigahertz is get attenuated. So, that cutoff frequency plays a very important role in determining all the condition, and this is calculated by the condition of the evanescence mode. So, what is the condition? Gamma g will be equal to 0, that this condition will be equal to 0, and when gamma g is equal to 0, we get omega square mu epsilon is equal to kc square, and this omega c, this omega will be replaced with omega c, which give our cutoff frequency. That is why it is replaced with omega c. So, when we take it as a 2 pi f c square mu epsilon is equal to kc square, which is equal to kx square plus ky square. Now, f c, this will be equal to 1 by 2 pi, and this will become this side under root mu epsilon, and this will be under root kx square plus ky square. So, you have to remember this formula because this is very important one and is used for calculating the cutoff frequency. Now, comes the second case. This is the case when the wave is propagating. The wave will be propagate when omega square mu sigma mu epsilon is greater than kc square, that is our wave number, and in that case there will be our attenuation propagation constant is alpha plus j beta. So, in this condition our attenuation will be minimum, that is why this propagation constant is related with the beta, and this is the condition. In this case our propagation constant is given by under plus minus j omega under root mu epsilon under root 1 minus fc by f ka whole square. And the third case is when the wave will be attenuated. So, what will be the condition? Just reverse of the condition. When the wave is propagating, omega square mu epsilon should be less than kc square, and this in this case this attenuation plays an important role. That is why gamma g is equal to plus minus alpha g, which is our attenuation constant, and in this is a real part. That is why plus minus omega under root mu epsilon within bracket f c upon f whole square minus n. So, when we talk about our propagation constant, three condition comes: cutoff, wave propagation condition and the attenuation condition. So, considering all this, for a wave to be propagated, the equation can be written as this: in the x x, y y remains the same, and z, where the wave is propagating, is replaced by e to the power minus j beta z, the case where wave is propagating, and all other cases ignored. This is the replacement of our z's function. So, here comes the end of the wave equation in the rectangular coordinate. We will continue with the next topic in the next class. Thank you for attending today's class.